In numerical analysis, Quasi-Monte Carlo method is a method for numerical integration and solving some other problems using low-discrepancy sequences. This is in contrast to the regular Monte Carlo method or Monte Carlo integration, which are based on sequences of pseudorandom numbers. Monte Carlo and quasi-Monte Carlo methods are stated in a similar way. The problem is to approximate the integral of the function f as the average of the function evaluated at a set of points x1, xn. Since we are integrating over the s-dimensional unit cube, each is a vector of s elements. The difference between quasi-Monte Carlo and Monte Carlo is the way the shear chosen. Quasi-Monte Carlo uses a low-discrepancy sequence such as the Halton sequence, the Sobel sequence, or the Fourier sequence, whereas Monte Carlo uses a pseudorandom sequence. The advantage of using low-discrepancy sequences is a faster rate of convergence. Quasi-Monte Carlo has a rate of convergence close to O, whereas the rate for the Monte Carlo method is O. The Quasi-Monte Carlo method recently became popular in the area of mathematical finance or computational finance. In these areas, high-dimensional numerical integrals, where the integral should be evaluated within a threshold epsilon, occur frequently. Hence, the Monte Carlo method and the Quasi-Monte Carlo method are beneficial in these situations. Approximation error bounds of Quasi-Monte Carlo. The approximation error of the Quasi-Monte Carlo method is bounded by a term proportional to the discrepancy of the set x1, xn. Specifically, the Cokes-Mallorca inequality states that the error is bounded by, where v is the Hardy-Krauss variation of the function f for the detailed definitions. Dn is the discrepancy of the set and is defined as, where Q is a rectangular solid in 0, 1, S with sides parallel to the coordinate axis. The inequality can be used to show that the error of the approximation by the Quasi-Monte Carlo method is, whereas the Monte Carlo method has a probabilistic error of, though we can only state the upper bound of the approximation error. The convergence rate of Quasi-Monte Carlo method in practice is usually much faster than its theoretical bound. Hence, in general, the accuracy of the Quasi-Monte Carlo method increases faster than that of the Monte Carlo method. Monte Carlo and Quasi-Monte Carlo for multidimensional integrations. For one-dimensional integration, quadrature methods such as the trapezoidal rule, Simpson's rule, or Newton-Cotes formulas are known to be efficient if the function is smooth. These approaches can be also used for multidimensional integrations by repeating the one-dimensional integrals over multiple dimensions. Cubature is one of the well-known packages using quadrature methods that work great for low-dimensional integration. However, the number of function evaluations grow exponentially as the number of dimensions increases. Hence, a method that can overcome this curse of dimensionality should be used for multidimensional integrations. The standard Monte Carlo method is frequently used when the quadrature methods are difficult or expensive to implement. Monte Carlo and Quasi-Monte Carlo methods are accurate and fast when the dimension is high, up to 300 or higher. Morakoff and Kaflish studied the performance of Monte Carlo and Quasi-Monte Carlo methods for integration. In the paper, Halton, Sobel, and Fourier sequences for Quasi-Monte Carlo are compared with the standard Monte Carlo method using pseudorandom sequences. They found that the Halton sequence performs best for dimensions up to around 6, the Sobel sequence performs best for higher dimensions, and the Fourier sequence, while outperformed by the other two, still performs better than a pseudorandom sequence. However, Morakoff and Kaflish gave examples where the advantage of the Quasi-Monte Carlo is less than expected theoretically. Still, in the examples studied by Morakoff and Kaflish, the Quasi-Monte Carlo method did yield a more accurate result than the Monte Carlo method with the same number of points. Morakoff and Kaflish remark that the advantage of the Quasi-Monte Carlo method is greater if the integrand is smooth. and the number of dimensions s of the integral is small. Drawbacks of Quasi-Monte Carlo. Lemieux mentioned the drawbacks of Quasi-Monte Carlo. In order for to be smaller than, needs to be small and needs to be large. For many functions arising in practice, we only know an upper bound on the error dn, and it is difficult to compute an. In order to overcome these difficulties, we can use a randomized Quasi-Monte Carlo method. Randomization of Quasi-Monte Carlo. Since the low-discrepancy sequence are not random, but deterministic, Quasi-Monte Carlo method can be seen as a deterministic algorithm or de-randomized algorithm. In this case, we only have the bound dn for error, and the error is hard to estimate. In order to recover our ability to analyze and estimate the variance, we can randomize the method. The resulting method is called the randomized Quasi-Monte Carlo method and can be also viewed as a variance reduction technique for the standard Monte Carlo method. Among several methods, the simplest transformation procedure is through random shifting. Let x1, xn be the point set from the low-discrepancy sequence. We sample s-dimensional random vector u and mix it with x1, xn in detail. For each xj, create and use the sequence instead of. If we have R replications for Monte Carlo, sample s-dimensional random vector u for each replication. The drawback of randomization is the sacrifice of computation speed. Since we now use a pseudorandom number generator, the method is slower.